Welcome back. Today, we're exploring deep learning, an advanced subset of machine learning. This technology is revolutionizing many fields from healthcare to entertainment. By the end of this video, you'll have a solid understanding of what deep learning is, how it works, and where it's applied. Deep learning uses neural networks with many layers, hence deep, to analyze various factors of data. It mimics the human brain's ability to learn from experience. Unlike traditional machine learning, which requires manual feature extraction, deep learning algorithms automatically discover the representations needed for classification or detection. Neural networks, and these are computational models inspired by the human brain, consisting of layers of interconnected nodes or neurons. Imagine them as a complex web of connections where each connection has a strength or weight that gets adjusted as learning happens. Layers. In deep learning, the term layers refers to the levels of processing the data goes through. Think of it like a multi-layered cake where each layer adds new flavors, or in this case, processes the data in new ways. Neural networks are the backbone of deep learning. They consist of layers of interconnected nodes or neurons that process and transform input data. Let's dive a bit deeper. There are three main types of layers in a neural network. One, input layer. This layer receives the raw data input. Two, hidden layers. These are the layers where the actual processing is done through weighted connections. Each neuron applies a function to the input and passes the result to the next layer. Three, output layer. This layer produces the final output, such as a classification label or a predicted value. Each connection between neurons has a weight, and these weights are adjusted during training to minimize the error of the network's predictions. Neurons. Think of these as tiny decision makers. Each neuron takes an input, processes it, and passes it on to the next layer. If the input is like a question, the neuron's job is to answer it and pass the answer along. Weights. These determine the importance of the inputs. In a way, they are like volume knobs that adjust how much attention the neuron pays to each input. Deep learning powers many modern AI applications, including image and speech recognition, autonomous vehicles, and natural language processing. Let's break down a few examples. Image recognition convolutional neural networks, or CNNs, are used to identify objects within images. These are specialized neural networks for processing data that has a grid-like topology, like images. They work by scanning the image with small filters to detect features like edges, colors, and textures. They are widely used in facial recognition systems, medical imaging, and even in apps that suggest photo filters. Speech recognition, recurrent neural networks, or RNs, and their variants, such as long short-term memory networks, or LSTMs, are used to transcribe spoken language into text. RNs are designed for sequential data like speech or text. They remember information about previous inputs, making them good at processing sequences where context is important. A type of RNN, long short-term memory or LSTMs, can remember information for long periods, which is useful for tasks like language translation. This technology is behind virtual assistants like Siri and Alexa. Autonomous vehicles' deep learning algorithms help self-driving cars understand their environment through object detection, lane detection, and path planning. Natural language processing, or NLP, techniques like transformer models such as GPT-3 are advanced models used for understanding language. They can process words in relation to all other words in a sentence, making them very powerful for tasks like translation and text generation. These models are used for language translation, sentiment analysis, and even for generating human-like text. For instance, Google's AlphaGo, which defeated the world champion in the game of Go, uses deep learning techniques. AlphaGo employs a combination of supervised learning from human expert games and reinforcement learning from playing large numbers of games against itself. This allows the system to learn advanced strategies and improve its performance over time. AlphaGo's success is a testament to the power of deep learning. The system uses two main neural networks, policy network and value network. The policy network predicts the next move based on the current board state. The value network evaluates the likelihood of winning from any given position. By combining these networks, AlphaGo can explore potential moves and select the most promising ones, even without explicit programming for Go strategies. While deep learning has achieved remarkable success, it also faces several challenges. Data requirements. Deep learning models require large amounts of data to train effectively. This can be a barrier for applications with limited data availability. Techniques like data augmentation, which artificially increases the size of the training data set by creating modified versions of existing data, are used to mitigate this issue. Transfer learning, where a model trained on one task is repurposed for another related task, also helps in scenarios with limited data. Computational resources training deep networks is computationally intensive and often requires specialized hardware like GPUs or TPUs. Cloud computing and specialized hardware like GPUs, which are graphics processing units, and TPUs, which are tensor processing units, are widely used to speed up the training process. Many companies and research institutions now provide cloud-based services to make these resources more accessible. Interpretability. Deep learning models are often seen as black boxes because it's difficult to understand how they make decisions. Improving model interpretability is an active area of research. Researchers are developing methods like attention mechanisms and explainable AI or XAI techniques to make deep learning models more transparent. These methods aim to highlight which parts of the input data the model is focusing on when making decisions. Despite these challenges, the future of deep learning looks promising. Researchers are continually developing new techniques to make models more efficient, interpretable, and applicable to a broader range of problems. Now, let's address some common questions about deep learning. How is deep learning different from traditional machine learning? Traditional machine learning often requires manual feature extraction, where human experts define the features that are most important for the algorithm to learn. In contrast, deep learning automatically discovers these features during the training process, often leading to better performance, especially with large data sets. Can deep learning be applied to any field? While deep learning has proven to be highly effective in many fields such as image and speech recognition, healthcare, and autonomous driving, its applicability depends on the availability of large amounts of data and computational resources. Some fields with limited data might find it challenging to implement deep learning effectively. What are some ethical considerations in deploying deep learning systems? Ethical considerations include ensuring data privacy and security, avoiding biases in the training data that can lead to unfair or discriminatory outcomes, and the potential impact on jobs and employment. It's crucial to develop and deploy these systems responsibly with transparency and accountability. Let us know in the comments what you think are the answers to these questions. Deep learning is at the heart of many AI advancements. From enhancing our daily lives with smart assistants to pioneering breakthroughs in healthcare, its impact is undeniable. Next week, we'll see how AI is used in everyday life, making mundane tasks easier and opening new possibilities. Subscribe and stay informed. Thanks for watching.